Hi, thank you for coming. My name is Michael Couch. I am an undergrad studying at California State University, Bakersfield. And the title of my talk today is Cooling Power Waste Evaluation Resulting from Malicious Thermal Measurements in Multi-Core Processors. We'll start off briefly by going over data centers, thermal management, and hardware trojans before getting into the experiment that I ran. Data centers are dedicated facilities for storing and computing data. They are made up of many servers that have many processors. The real numbers behind how much energy data centers use is unknown, as the only real numbers that are available come from mathematical models. But all the data that we do have suggests that it's in the range of terawatt hours and maybe even the range of petawatt hours. Some of the world's larger computing centers require about 100 megawatts of power capacity. An EPA study from 2006 shows that roughly 1.5% of total U.S. electricity consumption was due to data centers. And while these are estimates, what we do know is that cooling strategies are very important for mitigating power consumption. And they can reduce the power use anywhere from 33 to 50%, according to one study. So next, let's talk about cooling strategies. And there's two types of cooling strategies. Sometimes they're referred to as dynamic thermal management techniques. They are one is local, which utilizes heat sinks, water cooling, case fans, and that sort of thing. And as local cooling options fail to provide adequate cooling, centralized methods take effect, things like air conditioning in the building. And it's important to note here that local cooling measures rely heavily on thermal sensors, which are used to report the temperatures of the components. And next we're going to talk about hardware trojans. Software security is written with the idea that hardware can be trusted, but what if it can't be? Chip manufacturing is increasingly being outsourced due to cost. And not only that, but design and production are not always linked. And so what is a hardware trojan? It's a malicious circuitry design that's triggered to affect normal operation. And it can be triggered a number of different ways. All the time via complex logic gates, timing, and with the exponential increase in the number of circuit nodes, it makes them really difficult to find via regular testing. And so what are they capable of doing? They can modify functionality. Modifying stored data directly, affecting computation, and the possibilities are really limitless. And they're only really limited by the imagination and the abilities of the people creating them. They can modify specifications. They can change clock speeds. They can change power usage, geometry, and these sort of things can actually be coupled with the modified functionality. A lot of the time it doesn't really make sense to implement one vulnerability. They implement an array of vulnerabilities. They can leak information. So information can be transmitted without even the knowledge of the user. And one thing I found really interesting while investigating this is that they can hide information in the digital noise margins in the existing circuits, so you never even know that it was there under normal conditions. They can also just complete denial of service, anything ranging from degradation of the components to an immediate kill switch. And so let's go back to the cooling. Local cooling, like I said, relies heavily on the thermal sensor readings. What if there were a hardware trojan? Having unwanted modifications and the circuit design would facilitate this sort of attack. Also, permanent or transient faults just in the sensor or its accompanying circuitry. So with these improper thermal sensor readings, they can really go in two directions. Some of the literature has really shown, especially because of the degradation of the components, that if you subtract off some error from the actual temperature of the CPU, what are you really looking at? You're looking at a lower temperature than what's actually there in the processor, and this would lead to an inadvertent reduction in cooling efforts because the computer thinks that the temperature is higher or lower than it should be. And this obviously would lead to excessive hardware deterioration and failure. But what if, some error was added to it? And this would cause the system to report a higher temperature than what is actually there. And it would lead to excessive power waste, really. And what we're going to show you is how, in this scenario, it could result in power waste and basically steep financial costs. And so how did we do this? Well, this was my little miniature data center, in my room out of Bakersfield, California. I used a Raspberry Pi to model a one-server data center, an Amazon brand desk fan as my cooling strategy, and you can also see the relay there. It's actually in the center in the top photograph. On the bottom, it's kind of obscured a little bit by tape that I was using to kind of hold it down. But the IoT relay was toggled using the Raspberry Pi's general purpose input-output pins. And then we used power meters to measure the power output of the devices. Next, let's talk about the logic behind my controlling program. And first, we waited for the system to reach an ambient temperature. I chose 52 degrees because that's what was really working in my room in Bakersfield. If it were lower than this temperature, that would cause the CPU to do some work to bring it up to temperature, and if it were higher, then we cooled it and waited to begin the testing. And once testing began, infinite loops that performed floating point arithmetic were run on all 4 cores, which kept the CPU at or near 100% utilization for the duration of the experiment. The temperature of the CPU, as reported by the thermal sensor, was then read. And if it were a normal testing condition, then the CPU temperature was not modified. And if it were an attack condition, then either 10 or 15 degrees Celsius were added to the CPU temperature. If the temperature rose above a threshold, then the fan was turned on to deploy our cooling strategy. And if it were below the threshold, then the fan was deactivated. And power measurements were then taken every 10 seconds for the duration of the 10-minute test. The test was also repeated not only to cover all the experimental conditions, but also for distances of 1, 2, and 3 feet, where the fan was placed 1 or 2 or 3 feet away from the Raspberry Pi. And what did this result in? Well, the first measurement we really looked at was the average power reading during the test. You can see my graphs here. They're kind of organized and broken up by experiment. And so we have the top left where A is, we set the error to be 10 degrees Celsius. The threshold that the fan was activated was going to be at 75 degrees Celsius. And then the far left, the white and horizontally striped graphs were the normal and then the attack 3-foot conditions, and then going to the right, normal and attack 2 feet for the black and vertically striped, and then normal and 1 foot and attack 1 foot for the gray and diagonally striped columns. And this sort of pattern is repeated for both all three B, C, and D as well. We ran a 3-way mix ANOVA with attack distance and threshold as between subject factors against average power. And we found that there were significant main effects of attack condition, threshold, and distance. And a post hoc Tukey revealed that the normal condition significantly differed from 10 and 15, and the 10-degree error condition significantly differed from the 15-degree error condition. And this really wasn't surprising because, and this is what we expected, as we caused the fan to turn on more, it significantly increased how much power was being used throughout the session. The next measurement I looked at was power waste. And power waste is a measurement that represents the difference between attack and normal conditions, and it was cumulatively summed across the session. The attack condition, as you can see, always resulted in more power consumption than the normal condition, as noted by the fact that all the final points were well above the x-axis and continued to trend upwards, which again was what we expected. We then used the total power waste to calculate a percent increase in power. And here's a table that illustrates that calculation. And as you can see on the right-hand column, the percent power increase that resulted from our simple test shows that the simulated hardware Trojan has a drastic impact on power consumption. So in summary, the power consumption was significantly increased with the introduction of the simulated hardware Trojan. And power increased differently depending on the testing conditions and the cooling strategies employed. And in the most extreme scenario, the hardware Trojan nearly doubled the power output by the system, which would result in a proportionate increase in costs. And if we extrapolate this out to the size of a data center, it could mean substantial monetary losses. I'd like to thank Professor Delrahim for his guidance on this project. I'd also like to thank CSUB's Summer Undergraduate Research Experience program for funding this experience. So thank you very much. Here's my references. And thank you for your time.